My name's Dave Fenwick. I'm the system architect of Compaq Computer Corporation's next generation GS series Alpha server. In this section, we're going to discuss the logical design of the machine, how we made it modular and we made it scalable. Let's start with the basic building block of the machine. This is a quad switch backplane which implements a fully connected, non-blocking crossbar. The quad switch itself is implemented by many ASICs, in particular a control and several data path ASICs. It also has a full set of duplicate tags to track the cache line status of the CPUs. The reason we did this will be explained later when we start to expand this machine above 4 processors. The quad switch is used to interconnect CPUs, memories, and I/O. We're going to discuss how I/O interconnects in the machine later, so let's start now by taking a look at the CPU module. On the module we have the EV6 microprocessor, its board level cache, and an SROM. The reason we put the power supply on the CPU board is because as we increase the performance of the microprocessor, the power supply requirements change. If we'd had a central power system, this would have been very difficult to change and expensive. But as we upgrade the CPU boards, we also upgrade the power supply. Now let's talk about the memory module. It consists of an interface to the quad switch, which is implemented by 1 address control ASIC and 2 data path ASICs. This interface talks to the memory array, which consists of 2 separate arrays of 4 DIMMs each. This gives us 8 banks of memory, which we can 8-way interleave. With 4 memory modules in a quad processor, we can get 32-way interleaving. The capacity of the memory is 8 GB per quad with 4 modules, growing to 16 GB per quad with 4 memory modules, and eventually reaching 32 GB per quad with 4 memory modules. Now let's talk about scaling this machine beyond 4 processors. To build an 8-processor system, we just replicate the quad switch. We add a global port to the quad switch, which now allows the CPUs to communicate beyond their quad domain. We connect the global ports together with back-to-back cables through a scrambler module. The scrambler module is a simple passive module that allows the output cables of one global port to be routed to the input cables of the opposing global port. With this arrangement, a CPU in this quad can now read memory in this quad. However, there's a problem. If a CPU in this quad reads a cache line from memory in this quad, we can no longer maintain coherency. We solved this problem by adding a directory to each of the quads. The directory maintains the cache line status of the cache lines in each quad's memory. This system allows us to grow to 8 processors, and we can apply this system to beyond 8 processors. Now let's talk how we move beyond 8 processors. The quad switch, processor, memory, and I/O port, along with the global port and directory, form a unit called the quad building block. Now we can replicate the quad building blocks up to a maximum of 8. This would yield a 32 processor system. The decision we had was how to interconnect the quad building blocks. We could use a bus, but the problem with the bus is it's a shared resource. And shared resources don't scale as we add quad building blocks. So we decided to interconnect the blocks with a second level switch, which we called the hierarchical switch. This switch now allows us to linearly scale resources within the system as we add more quad building blocks to the system. Let's talk about quad switch data flow and local latency. If a CPU wants data from memory, it sends an address to the quad switch. The quad switch routes it to the appropriate memory, which then returns data. The returned data is then routed by the quad switch to the requesting CPU. Now, multiple CPUs can make multiple requests to memory. So as more and more transfers take place, the quad switch continues to field the requests. These requests take place in the minimum amount of time, which is called minimum local latency. When a CPU in this quad building block wants to access memory in this quad building block, the time it takes is called the global or remote latency. Now it's important to realize that it's always going to be longer to get to this memory than, for instance, a CPU to this memory. The ratio between the global to local latency is a very important ratio. And we decided that if we maintained that ratio at 3:1 or less, the performance of this system would be excellent. To achieve this, we used the hierarchical switch to switch between the quad switches. Let's take a look at conceptual flow within this machine. First, let's get this quad moving. Let's get local transactions between CPU and memory. Now let's start bringing more transactions in all the local memories. Now this would be a nice situation, but reality is that of course global traffic has to take place. So we can have transactions between here and here, here and here. Let's put this global memory system in motion. Now as you can see, not only is this quad talking within its own memory, but it's also talking to memory here, 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 and here. It's the ability of this machine to allow both local and global traffic to keep moving and keep going and not be stalled that gives us the excellent scaling attributes that we needed for this system. As promised, we're now going to discuss the I/O. The I/O is connected into the quad switch by an I/O port controller. The I/O port controller has 4 I/O channels. Each channel is a 256 megabyte per second full duplex I/O channel. We wanted to connect these I/O channels to a remote I/O subsystem. The reason is that on a large server which connects to an enormous amount of storage, you need spatial separation of the I/O subsystem from the system box. To achieve this, we have to drive cables. To drive cables, we take the I/O channel and pass it to an ASIC, and this ASIC does protocol and voltage translation, which allows us to drive 10-meter cables to our I/O subsystem. Let's move to the other end of the cable. We have an ASIC. It does voltage and protocol translation. It talks to a PCI interface. Now, we could have just done one segment of PCI interface, but we have enough bandwidth on this I/O channel to actually support 2 segments. So we decided to support 7 slots of PCI on 2 segments with this PCI interface. Now, we looked at the cost of building this remote I/O subsystem, and we decided that it was more cost efficient for our customers for us to supply another I/O channel with another 7 slots of PCI in that box and amortize the cost of that box across more PCI slots. The system can support multiple quad switches with multiple IOPs with multiple PCI boxes. In fact, we can put in a 32 processor system 16 of these 14 slot PCI boxes, which gives us 224 slots of PCI. And in a large, complex solution that we intend to use the GS AlphaServer for, the large number of PCI slots across the system is absolutely key. We've reviewed the logical design of this server. It's the physical implementation of this logical concept that yields the next generation GS series AlphaServer.